All right, so thanks everybody for joining today on this April 13th. I know we're starting to get towards the end of the semester for this, or end of the semester, so I know things are a little bit busier, class projects, and especially with it being the end of the year, a little bit more, it's a little bit busier of a time, less time to do things here and there. So thank you for joining, and I do know there's a couple of teams that have been asking and people have presented before. I am still very much behind on posting these videos to our YouTube channel, and I will look to do that, start doing that for ones back in January already. That's how far backlogged I am, but do that tomorrow or Friday, and then try to catch up some more next week. But otherwise, I think after today, I think there's only one more session for the semester. As I say, we're really getting towards the end of the semester. So there's one in 2 weeks, and then I think the week after that is is right before reading day. So we're really kind of coming towards the end here. But without further ado, we'll have Mark Munson, who I wanted to get it correct. You're a PhD candidate. Or
just masters.
Just masters? Okay. Okay. No, it's totally fine. I was the same. So as a graduate student, though, in the AOE department, with an advisor of Dr. Black.
Dr. Ross.
Dr. Ross. Okay. Sorry, I've worked with Mark on a few other things in different contexts. So, but yeah, very, very, very good. But yeah, he's going to present today on the collision avoidance and via the orbital right of way. So try to not mess anything more up for you, and let you take it away.
Great, thank you, Kevin. Good afternoon, everyone. And I'm Mark Munson. I'm a second year aerospace engineering graduate student. I'm doing the thesis option, as Kevin mentioned. My advisor is Dr. Ross. Dr. Black is on my advisory committee, so that's my connection to him. What I'm going to go over today is well, this is, I submitted an abstract to present a paper at a conference, an AIAA conference in August. Hopefully it gets accepted. Keep your fingers crossed. This presentation will be centered around that paper. It'll be mostly high level. I have one plot, so it's not going to be like overly technical because a lot of the stuff is still in development as I kind of piece everything together. The title is Collision Avoidance via Orbital Right-of-Way, and I will explain that as we go further into this presentation. General outline, background, go through a quick literature review, talk about some assumptions I've made, my planned methodology and approach, and then future work I intend to do and some challenges I've identified that I'm going to have to work through. So background to this topic, many of you are probably aware of the orbital environment around Earth is increasingly getting more and more crowded, not just space debris, but active satellites. And you might have heard or recall an incident that occurred a couple years ago, September of 2019, a SpaceX Starlink satellite almost collided with a European Space Agency satellite. I think it was primarily a science satellite, AOS. Generally, what happened was, they nearly collided, and Starlink has an autonomous collision avoidance system. So there was this back and forth between the space operators at ESA and Starlink about who's going to do what, and you can kind of see in what I've got highlighted here. The whole thing was done through emails. It's you kind of like imagine, you're driving down a highway and you're shouting at an oncoming car, like who's going to get out of the way. So as you can imagine, this situation is untenable. And so my whole goal is to try to design or come up, if it's possible, a way to designate right away in orbit. This is another example. The current state is that different organizations will do their own agreements. So this right here is an agreement between NASA and SpaceX, where I pulled out one line there, which I thought was kind of interesting, where NASA has agreed not to maneuver an event of a conjunction to ensure not inadvertently maneuvering into one of SpaceX's satellites. And as more and more players get in orbit, you can't, this memorandum of agreement for every single person isn't going to work, because everybody's going to be operating off of different assumptions and different rules, and there'll be collisions. So you need a standard. And I'm sure you've all driven and you're familiar with right of way and all that, but I just kind of threw this up here just to make sure people understand what I'm saying. They're basically arbitrary conventions to prevent collision, prevent loss of life, property. You have on the road, you have it in the air, you have it on the water. The schematic on the right is just kind of like a maritime example of right of way. And the goal, as I said, is to apply a model to orbit around Earth. And I'm sticking with Earth right now, even though space traffic in cislunar space, and you probably see articles about, the moon, the Air Force wants to put up constellations around the moon. A lot of different countries are now, they have activity going on the moon. My goal is to first stay simple with the Earth, because as I move out, the model will become more and more complicated. So if I try and do this first, and then maybe it could be extrapolated out to cover more situations. So literature review, there's a ton on just collision avoidance in general. Probability of collision is a big thing. But in my assumptions, as you'll see when I get into the methodology, is I assume a risk of collision exists. So I kind of sidestep the probability of collision question. But there's a lot about optimal maneuvers around space debris. But at least I haven't found a whole lot on attempts to try and create some kind of system that will designate right away. And if you read a lot in the news and stuff, you have a lot of you see a lot of policy. They talk about, well, we have to establish, they say norms, rules of the road, rules-based system in orbit too. So you prevent collisions, avoid the Kessler syndrome, and it's from all the UN General Assembly resolutions to news articles. So it's a big topic, something that needs to be solved. But as far as I can tell, there hasn't been a whole lot of actual research done on it. I have found one paper down the bottom, rule-based cooperative collision avoidance using decentralized model predictive control, that looks at it generally. It doesn't try to apply it to a specific domain, but they define what's called a heading rule and a velocity rule, which basically based off an angle of the velocity vectors, it'll determine whether if you slow down or maneuver around the other vessel. So that's the only technical paper I found that kind of addresses what I'm looking for. So that's a big disadvantage. There's not, as far as literature review that I've found, there's not a whole lot of prior work done. So these are my assumptions. It's a two-body model, no perturbations. As I said, I'm just considering the Earth. I'm not worried about the sun or solar rays or anything like that. spacecraft model with point masses. I'm assuming they're all maneuverable and cooperative. So I'm not, in this, I'm not concerned about space debris. It's just, satellites that can maneuver. And I'm assuming eccentricity is close to zero or near the eccentricity of the orbits that the satellites are in are zero or near circular. And that's important as I try and simulate this because I want to use the Hill-Cholessy-Wiltshire equations of relative motion. That's the key assumption for those equations. I assume a risk of collision exists. So this on the bottom, that's an ESA standard. So they assume a collision will exist if probability of collision exceeds 1 in 10,000, or if a radial separation between one of their assets and another asset is less than 100 meters. So now we'll go into my methodology and approach. This is also still kind of a work in progress. I'm kind of at like 3.5. So, but I mean, I'll show you a little bit about what I plan to do for 5. So essentially, I define what's called a CPA, a closest point of approach. So it just basically take a position vector from the center of the Earth to the point predicted as to where the two satellites, their closest point of approach. If you're familiar with the literature, one term they use is close approach. That's kind of like a legacy of the pilots. That's a term they use in aircraft. I find that to be kind of vague, so I like closest point of approach because that it clearly defines like, okay, this is where the closest point that there will be. So I just like that term better. So I define a CPA and I just make a unit vector out of that. And that will play a role in how I define my coordinate frame, which will be used to apply my maneuver rules and then simulate using the relative motion equations to see if it works. So the maneuver section I take, it's just basically the span of the velocity vectors from each satellite, M1, M2. And that's how I can define my orthonormal coordinate frame for this process. And if you're familiar with Gram-Schmidt, it's maybe from your linear algebra class, it basically is a method that you can take any 3 vectors and transform them into 3 other vectors in an orthonormal basis. And then you can easily change each one of those vectors into a unit vector, and that's your coordinate frame. So you begin by just choosing your first vector, and that is, you accept it as it comes. So in this case, for the 2 satellites, V1 and V2 are your first 2 unit vectors. So you see here, just turn the first velocity vector into your unit vector, and then do the Gram-Schmidt process for the second velocity vector, and you're just basically subtracting the projection of the second velocity vector from the second velocity vector, and that gives you that yellow perpendicular unit vector. So that gives you, you have your first M1 hat, M2 hat, and then you can just easily, to get your third unit vector for your orthonormal basis, you just do cross product. So M3 hat equals M2 hat cross M1 hat, and there you have your coordinate frame with your CPA at the origin to apply your maneuver rules to. This is the one plot I referred to. I was able to implement this on MATLAB. So basically, I wrote a code that you can just take, it'll take in any number of velocity vectors and transform them all into this coordinate frame here that you see. There are a couple things I have to work on it, but the general idea is when I have this unit vector or this coordinate frame defined with the CPA at the origin, the hope is that I can use this, somehow integrate it into the relevant motion code that I'm going to write or try and write, and then that's how I can simulate it. So this is kind of like an eye chart, but these are, if you look on the left, number 2, the maneuver rules. That's what I'm going to try first. It's just basically like a vector. Just define a vector, and based off what you get, and you can kind of just arbitrarily say, okay, this one's give way, this one's stand on. The cosine formula version is adapted from that paper I talked about the heading and velocity rule in the literature review. I'll try that too. But I mean, the thing about this is it's all arbitrary. So I've gotten some comments where it's like, well, why this way? Why not that way? Well, it's arbitrary. I'm just trying to define some method of maneuver that people can predict so that there's not a bunch of guessing as to what this satellite orbit is going to do. So, I want to simulate it and just kind of see what happens. And what I'm going to do is create several scenarios going from simple to a little more complex and just see what happens. So the first one I want to do is just 2 spacecraft converging to the CPA, 1 maneuvers away. Scenario 2 would be something like 2 spacecraft converging, 1 maneuvers out of the way, but then it maneuvers into the path of another spacecraft, and then you have another scenario, another collision scenario. In scenario 3, it would be some like combination of 1 or 2 or just 2, but with more spacecraft. So that's kind of the goal. And I haven't gotten to write, I have a general idea of how I'm going to write this code. But I think the hard part will be trying to integrate the generation of the coordinate frame. And I'm not sure how I'm going to do that and integrate it with HW code. So that's going to be one of the more difficult things. So as you can see here, it's still pending. I haven't gotten to that yet, but I have until August, so I've got some time. Future work, as I mentioned, I need to implement HW solver, implement the maneuver rule, and integrate the code, run the scenarios. Challenges, well, they might not work, so then I'll have to go back to the drawing board, try and design some other, I'm trying to keep it simple, simple, something like this, it should be simple. It shouldn't be some complex math formula. So that's kind of what I was trying to do, with just keep it at like a cross product in the maneuver rules or some kind of angle definition that's just kind of like easy to understand. Other challenges are, I'll continue to do lit review, but research is scant. And that's about it. I touched on the other ones. I might try and simulate this SDK, but that might be a little harder because it's kind of more like preset in what you can do with that. So I don't know. These are my references. Not, as you can see, not a whole lot. And that's it. And I'll take comments or questions.
Any comments or questions? You did kind of warn me, Mark was kind of warning me, this is a little bit of a shorter one, but it's good. It's good way to think of that. It was, I'll maybe start off with one, going back to the boat example. I'm familiar with that from a while ago with doing some boating and things, but are there cases, I could see where there's cases, right, where you're going across or going head on. Maybe not as much head on, but is there ones where you're doing orbits where you can see it's much more like an overtaking, it's coming much more behind kind of thing? Are there orbits that line up with that you're familiar with or know of?
I did consider that, and I think because if you're close to another satellite, like unless if you're like actively thrusting, you're going to be at the same velocity. So there's not going to be overtaking like in a boating situation. I would assume, they're not good because propellant is precious up there.
Yeah.
You're not going to be thrusting for a very long time.
Yeah.
Now, I mean, if you're, I'm just kind of, my goal right now is just kind of like the general traffic problem.
Mhm.
But I could see that becoming applicable when there's a bunch of like RPO, rendezvous and proximity operations going on. When you are close, you are kind of doing periodic thrusts as you're doing like a natural motion circumnavigation or like a forced circumnavigation around the body that you're in relative orbit around.
Yeah. Yeah, I guess I asked some of that too, if that ends up being, and I don't know if it would be ever helpful, but if that's like another assumption that you can add on, that like you're never going to have the case where your angles are pretty much like zero kind of thing. Like if that ever helps, they say like, well, I'll make the assumption that they're never, the projection is basically not going to be nothing. That they'll always have like some kind of projection there. There's a difference between the two vectors.
No, that's a good point. And well, that's just, I actually have them written down on hand drawings, but I just hadn't had a chance to like kind of put it into like PowerPoint. But I did kind of define a couple like basic scenarios, kind of similar to your point.
Yeah.
And then that was kind of maybe another way I attack the scenario problem is just create a bunch of combinations of those basic scenarios and see what happens.
Yeah.
But that's a good point.
Yeah. Any other questions from the folks that are online? Give the awkward pause to try to reach a mute button on Zoom. Okay. Well, otherwise, thank you very much for the presentation. It's very, it's a very interesting topic. Like I said, there's a lot of, I'm sure we could, I don't want to go through that where it's every scenario, think about every scenario that you could dream up and what happens here and what happens with this, right? Like, there's probably, we could spend, way longer than what's productive trying to go through that in this setting, kind of thing without, being able to do it on a whiteboard. And me being more knowledgeable, I'm sure too. But thanks very much to Mark for presenting and bringing this, and as well to the people online. Yeah, seeing some thumbs up, but let's go give the in room a round of applause here. So, and like I said, we'll have another seminar coming up in 2 weeks, and I'm not as good. I've been kind of slammed last week and this week, so I'm not as familiar on who's coming up in 2 weeks. But I do know that we have somebody booked for that. So look for the announcement for that. And everyone have a good day. We'll see you then.